Today we're looking at Unit 9, Bits, Bytes, and Binary. So Lesson A will be understanding bits, bytes, and binary. So we'll learn what bits and bytes are, and we'll learn about the binary number system. Okay, so bits, bytes, and binary. Binary is a number system where digits have only two values, 0 or 1. Remember that we normally use the decimal number system, where the digits are 0 to 9. A bit is the smallest unit of information. It can only be a 0 or a 1. It represents the state of one switch. If the switch is off, then the bit has the value 0. If the switch is on, then the bit has the value 1. Okay, and again with the decimal system, our smallest unit of information is 1. But then it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay, a byte is a sequence of 8 bits that represents larger pieces of information. It can represent any value from 8 zeros through to 8 ones. So each digit in a byte can be thought of as representing an individual switch that is either off or on. Okay, so if we look over here we've got a bit. It can either be 0 or 1. Here we've got bytes, and this byte is all zeros, this byte is all ones, and you can have any byte from 0 to all ones. So if you're counting in the binary number system, you start at all zeros, then you have 0, 0, 0, 0, 0, 0, 0, 1, then 0, 0, 0, 0, 0, 0, 1, 0, then 0, 0, 0, 0, 0, 1, 1, and so on. Okay, here we see switches that represent a byte. So this switch is on, that switch is off, off, on, off, off, on, off. So it represents this byte. Okay, packed transistors. Modern computer processors are made up of billions of tiny on-off switches called transistors. But information is still represented in essentially the same way, as a series of ones and zeros. Using binary allows computers to represent information simply and efficiently. Encoding the ones and zeros of bits and bytes can be used to represent letters, numbers, and even different keys on a computer keyboard. Okay, this is just a photo of some old transistors. You can still find transistors that look like this. Okay, a bit can be used to hold a Boolean true-false value. A value of 0 represents false, and a value of 1 represents true. And you remember in our previous unit we were talking about Booleans, so I said that true and false can also be a 1 and a 0. Okay, so these are some useful terms. A bit, of course, is a binary digit with two possible values, either 0 or 1. A byte is a sequence of 8 bits and has 256 possible values, from all zeros through to all ones. Okay, where do we get 256 possible values from? A number will have columns. The first column is 2 to the power of 0, which means it can be 0 or 1. The next column is 2 to the power of 1, which means that it's either 0 or 2. The next column is 2 to the power of 2, so it's either 0 or 4, and so on. So if you add all of that up, you get 256. Okay, we've also got kilobyte. Kilobyte is 1024 bytes, or 2 to the 10 bytes. A megabyte is 1,048,576 bytes, or 2 to the 20 bytes. A gigabyte is a billion bytes, 2 to the 30. A terabyte is roughly a trillion bytes, or 2 to the 40 bytes. Okay, so here we've got a binary vending machine. There's a vending machine that sells items of all prices. The machine cannot give change, so you must pay in exact amounts. You have one of each coin, 1, 2, 4, and 8 units. Okay, so you've got these coins. This is like 1 cent, 2 cent, 4 cent, and 8 cents, let's say. So create your own vending machine selling different items that cost 1 to 15 units. Try buying different items from the vending machine. Okay, so we're going to have a make-believe vending machine where you can put in these coins. These are the only coins you've got. You have to see how to make up each of these numbers. So what is the price of the least expensive item you can buy? Okay, so that's going to be 1 unit. So this item here is 1, so you use your 1 unit coin. What is the price of the most expensive item you can buy? Okay, you've got 4 coins. One is worth 1, one is worth 2, one is worth 4, and one is worth 8. So if you add them all together, it's 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So the most expensive item you can buy is 15. What else can you buy? What coins would you use to do this? So you'd use your 1 coin for this, you'd use your 2 coin for that, you'd use your 4 coin for this. How do you get this? You use your 1 and your 2 coin. So 1 and 2 together is 3. To get this costs 5, so you use your 4 coin and your 1 coin. And so on. What is the price of something you cannot buy because you don't have exact change? Well, if you work through all of these, you'll see that 6 is 4 plus 2, so you can buy that. 7 is 4 plus 2 plus 1, so you can buy that. 8 is your 8 coin, so you can buy that. 9 is 8 and 1. 10 is 8 and 2. 11 is 8 and 2 and 1, and so on. If you check all these values, you'll see that you can buy anything. So you do have exact change for all of these items. Okay, so if we add 2 more coins to your set of coins, what is the next logical coin denominations and why? Okay, so we had 1, 2, 4, and 8. Okay, so the next denomination would be 16, and the next would be 32. What is the new maximum price you could pay for an item? Okay, add them all together. So it's 16 plus 32 plus 8 plus 4 plus 2 plus 1. That gives you the most expensive item. Okay, so these coins are using the base 2 number system. Each place value is 2 times the previous one. Okay, so in our binary vending machine, now you use 1s and 0s to represent the numbers instead. You draw a table for your coins in descending order with 2 rows, one representing 0 and the other representing 1. How would you represent the number 45 in this system? And try calculating different numbers in binary base 2 notation. Okay, so let's take this table. So our lowest denomination is 1, then 2, 4, 8, 16, and 32. This is the same as 2 to the 0, 2 to the 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, that's 2 squared. 2 to the power of 3 is 8. 2 to the power of 4 is 16. Okay, 2 to the power of 4 is 2 times 2 times 2 times 2. So that's 16. And 2 to the power of 5 is 32. Okay, so to represent the number 45, we take 32 plus 8 plus 4 plus 1. Okay, so in binary, that would be 1, 0, 1, 1, 0, 1. Okay, and if we're using a byte, for some reason they've left off the other 2 digits. A byte is 8 digits. So then you'd have 0, 0, 1, 0, 1, 1, 0, 1. Okay, so we've learned about bits, bytes, and binary. So for our exercise, we'll code a binary transmogrifier, and then we'll take a quiz. Okay, so we're going to code a binary transmogrifier. Okay, so the exercise is to code a binary transmogrifier. In this activity, we will create a binary transmogrifier with the microbit. The user will be able to use the buttons to enter binary 0s and 1s, and will be able to press A and B buttons at any time to display the decimal equivalent of the number that has been entered. Okay, so first let's think about the algorithm we need to transmogrify a binary number into a decimal number. What is the pattern? When you add a 0 to the end of a binary number, how does the decimal value change? When you add a 1 to the end of a binary number, how does the decimal number change? Okay, so let's look at this. A binary 1 is the same as a decimal 1. Decimal 2 is binary 1, 0. Decimal 3 is binary 1, 1. Decimal 4 is binary 1, 0, 0, and so on. Okay, and again, they've stopped at 14, but if we have 1, 1, 1, 1, that would be 15. Okay, we can't have 16 with just 4 digits, so to have 16, we'd have to have 1, 0, 0, 0, 0. Okay, so what's the pattern? With each new binary number, how can you figure out the new decimal number? Okay, so we're going to say that button A is 1 and button B is 0. So if you press 1, then we get a 1. If you then press 0, then you get 2. If you press 1, 1, you get 3. If you press 1, 0, 0, you get 4. 1, 0, 1, you get 5, and so on. Okay, so write out pseudocode for your program first, then code it in MakeCode. So what happens when 0 or 1 is added to the end of a binary number? Okay, hints: create variables for the binary and decimal values. For the binary variable, use a string type to hold the sequence of 1s and 0s. Button A pressed, add a 1 to the end of the binary string. Button B pressed, add a 0 to the end of the binary string. Okay. So we're going to have a variable that we call decimal, and we'll set it to the number 0, and we'll create a variable called binary, and we're going to set it to an empty string. Whenever someone enters a 0, the new decimal value is twice the previous value. If someone enters a 1, the new decimal value is twice the previous value plus 1. So that's how we're going to calculate our decimal value. So the program might look something like this. So we're saying that button A is going to be a 1. So when you press button A, it's going to set our binary string to whatever the value of binary was, which starts off as a space with a 1 after it. Okay, we'll display the string, so we should see space 1. And then we're going to set the decimal, the variable decimal, to 2 times what it had been before, plus 1. Okay, so every time you enter 1 by pressing the button A, it will show our binary value, and then it will calculate the decimal value by multiplying by 2 and adding 1. Okay, if we want to enter zeros, we use the button B. So here we add a 0 onto the end of our string that we've called binary. And then we show the string, and then we have to set the value of decimal to 2 times the value of decimal. We don't add a 1 because B is our 0. Okay, and then whenever we press A and B together, it would show the value of our number. Okay, and then these are just some modifications we can do once we've made our basic program. We add a way to clear the binary and decimal values so you can start over, add a way to erase the previous value, create a decimal binary converter that allows you to enter a decimal value and see the binary equivalent when you press A and B together, and create a physical housing or case for your binary transmogrifier. Okay, so you can make a box to hold the microbit. Okay, so let's open a browser and start coding. Okay, so we're going to create a new project. Let's call it Unit 9 Transmogrifier. Okay, so to start, we're going to create those two variables. We'll have one variable that we call binary, and another variable that we call decimal. Okay, when we start, we'll set decimal to 0, and we'll set binary to an empty string. Okay, next, button A. When we press button A, we're adding a 1 onto the end of our number. So whenever we press button A, we have to take our variable binary and set it to, we want to join two strings. Okay, so we're going to take the variable decimal, the variable binary, and we're going to add a string on the end, and that string is a 1. Okay, so when we press button A, we're going to set, set binary to binary with a 1 at the end. We're then going to display it. Okay, binary is a string. So we'll show the string binary. Then we need to calculate the value for decimal. And we said decimal will be 2 times its previous value plus 1. Okay, so we need to do some math here. We're going to take times. So decimal is going to be the previous value of decimal times 2. Okay, but I need to add 1 to it. So we're going to take decimal is going to be decimal times 2 plus 1. Okay, so let's just test this now. So when we press button A, it's going to put a 1 at the end of the string binary, and it will display it, and then it will add 2 times. It will multiply the value of decimal, which starts off at 0, and add 1 to it. There we see 1. Here we see 1, 1. Okay, so let's take button B. Button B is going to do more or less the same thing. It's going to put a 0 at the end of binary. It will show the value of the new binary, and then it will multiply decimal by 2, but it will not add 1. So we can just duplicate all of this. This is now going to be button B. Okay, so we'll put a 0 at the end. We'll show the new value of binary, and we're going to set decimal to 2 times decimal. Okay, we don't need to add 1 this time. So we just multiply decimal by 2. Okay, so now when we press A, it displays a 1. If we press B, it displays 1, 0. We press A, displays 1, 0, 1, and so on. Okay, and finally, we want to see the value of decimal. So we'll say with A and B pressed, let's just show the string binary again, just as a reminder. And then we'll show the value of the decimal version. Okay, and let's just separate these two with something. Let's say a little dash. Okay, so it will display binary, a dash, and then the number. Okay, so let's try this. If I start with a 1, then we've got 1, and then I put in a 0, so now it's 1, 0. And I'll do another one. It's 1, 0, 1. Okay, what is 1, 0, 1? That should be 5. So let's see what we get. 1, 0, 1 is 5. Okay, so that's correct. Okay, I can carry on adding to it. So I had 1, 0, 1, so let's have 1, 0, 1, 1. It's 1, 0, 1, 1. So that's now going to be 1, 0, 1, 1 is 11. Okay. Right, so that's our transmogrifier. I can save that and go back to home. Okay, time for a quiz. So what is the definition of a bit? A binary digit with two possible values, 0 or 1. What is the definition of a byte? So a byte is a sequence of binary digits made up of 8 bits. It has 256 possible values from all zeros to all ones. What is 37 in base 2? It's 100,101. How do we work that out? It's 32 plus 4 is 36 plus 1 is 37. What is 110,110 in base 10? 54. Okay, so that's 32 plus 16. Okay, 32 plus 16 is 48. Plus 4 is 52. Plus 2 is 54. How are binary numbers calculated? Binary numbers are calculated based on the number of place values. Bits, as you enter ones and zeros, the value changes. Okay, and put the following in order from smallest to largest measurements. Okay, so kilobyte is 1,000 bytes, megabyte is 1,000,000 bytes, gigabyte is 1,000,000,000 bytes, and terabyte is 1,000,000,000,000 bytes. So what we learned today, we coded a binary transmogrifier. Okay, and for a project at home, you can try to make a binary cash register. Okay, so you want to try to make a binary counter and code it to display the decimal values of the numbers counted. So here we've got a binary cash register. The unplugged activity in lesson A uses a vending machine as a model for creating different combinations of binary place values. We found that for n coins, there is one and only one way to make every number between 0 and 2 to the n minus 1. invent a paper and cardboard version of the binary counter, then program it to display the decimal value of those numbers. Project example. This design uses coins and copper tape on a piece of cardboard. To indicate off or 0, the coins are flipped down. To indicate on or 1, the coin is flipped up so it lays flat across both pieces of copper tape, completing the circuit. So the microbit can detect that the connected pin has been activated. It calculates and displays the decimal value of the binary number that is indicated by the coins. Okay, if you look at this, here's our microbit. We've got P0, P1, and P2. We've got copper tape. So this is a conductor. And we've got ground here, going down here. And it goes to copper tape going across like this. And there's a gap between the copper tape to the pin and this copper tape here. So if you take your coin and you put it here, it closes the circuit to this pin. So this one is closed, so that's a 1. This one is open, so it's a 0. This one is closed, so it's a 1. So use a design thinking approach and ensure the project meets these specifications. It uses binary in a way that's integral to the program, uses mathematical operations to convert decimal to binary. All binary numbers display correctly, and the program compiles and runs as intended, and includes meaningful comments in the code. Hence, the microbit only has 3 pins, so your binary register is limited to 3 place values. You will need to use a strip of copper tape connected to the ground pin for the other side of the circuit for all 3 pins. The modifications you can try is write some code that will display the number in binary when you press the A button. Think of a way to create more place values, perhaps using a second microbit and a radio connection. Okay, our next section is on radio, so don't worry about this yet. We'll be looking at radio in the next unit. Okay, in case you didn't see the photo clearly, these are our pins P0, P1, and P2, and this is the ground pin. So ground pin, you've got copper tape like this, and then copper tape like that, like that, and like that, and there's a gap here. So if you put a coin across here, it connects ground to pin P0. Here the coin is not there, so pin P1 isn't connected to ground, and here pin P2 isn't connected to ground. So this is like a 1, 0, 0. Okay, so that's a binary cash register. Okay, so next time we'll be doing Unit 10, radio communications. So I'll see you then.